The last section of this video series with logarithms, we're going to start talking about what is the domain of a logarithmic function just by looking at it analytically as opposed to geometrically. Recall that if we have log base b of x as a function, then we just want to make sure that whatever's inside of that logarithm, or the component that's going to be the independent variable, we need to make sure that that expression is greater than 0. So for instance, if we have f of x equals log base 2 of x, or log base 2 of 3x plus 4, all we're going to do is just set 3x plus 4 to be greater than 0. And when we solve that, we're going to subtract 4 from both sides. And then finally, we're going to divide by 3. And so we get that x is greater than negative 4/3. And as an in the interval notation, since x is bigger than that, that would be from negative 4/3 to infinity. All right, so that's how we find the domain of a logarithmic function. Just whatever's inside of your parentheses, that's the independent variable. That stuff has to be greater than 0. A second example, x over 3 minus 2. All right, so all we're going to do, we're just going to set that greater than 0. We're going to add 2 to both sides. And then we're going to multiply both sides by 3. So that would be our domain for this. And since x is greater than 6, our interval notation would be from 6 to infinity. Third example, 3 ln of root x plus 3 minus 4. So again, this has to be greater than 0. So root x plus 3 minus 4 greater than 0. To solve this equation, we add 4 to both sides. We square both sides to get rid of the square root. So x plus 3 is greater than 16. And then we just subtract 3 from both sides. And so we end up with x is greater than 13. Okay, or in the interval notation, 13 to infinity. A fourth example, x squared plus 1 for ln. All right, so just worry about what's inside. And so x squared plus 1 greater than 0. We subtract 1 from both sides. So x squared is greater than negative 1. And if we tried to solve this, unfortunately, we can't solve this because if we take the square root of both sides, that would give us something like this number would be non-real, a plus or minus I, right? So if you ever get a non-real answer for your inequality, what that means is that there is no solution or there are no numbers to where this is not true, okay? And think about this. If you were to plug in any numbers into x squared plus 1, this number is always positive, right? X squared plus 1 or 0. And then this is a positive number. So a positive plus positive is always greater than 0. So this is always true. And so the domain for this function would be all real numbers. Okay, there's no number that we can't plug in that is not going to give us some sort of output. And looking at the graph, if we were to graph this thing, so let me close all this stuff out. This is a way we can verify that. We could say ln of x squared plus 1. And I want you to notice that this function is continuous, okay? There's no asymptotes whatsoever, okay? So that's actually pretty cool that we can see both geometrically as well as algebraically the domain for this function, okay? And just as another example, I can go back to the previous, and I can see that the domain for this function will be greater than 13. So let me just show you that one real quick, and then we can do our final example. So that would be 3 natural log of, what do we have, root x plus 3 minus 4. The square root of x plus 3 minus 4. And then I think it was plus 7 or something like that, plus 7. I'm going to zoom out on the graph, and clearly we can see that our asymptote, remember we had this 13, that just shows us that that is indeed going to be the domain of the function. All right, so that's how you can check it graphically on your calculator. It's just by graphing the function and then just making sure that what you got makes sense in the graph. All right, now, one last example. This one looks almost identical to the previous, except that we have an x squared minus 1. All right, so what this tells us is that we have to set this greater than 0. All right, And this is one where we have to use that critical value method that we saw in a previous section. So what we would do is we would factor this into x plus 1, x minus 1, and we get two critical values. Our critical values are -1 and +1. Okay, so that's our critical values. And you probably recall that we need to go ahead and break this up into intervals. All right, so just like we did in the last section, we have a -1, we have a +1. And so our test values are going to be -2, 0, and 2, or any numbers in those intervals. And our intervals are going to be from -1 to or negative infinity to -1, -1 to 1, and then 1 to infinity. Okay, so you probably remember that we had this table where we had the interval. So we had negative infinity to -1, and then we have -1 to 1, and then finally we have 1 to infinity. All right, and notice all parentheses because it's greater than, not greater than or equal to. Test value, that's going to be, like we said, -2, 0, and 2. And then we're just going to substitute that back into x squared minus 1, right? And we know that if we substitute -2 back in, that's -2 squared minus 1, which is 3, which is greater than 0. And so that's a valid statement. And remember, we might have like in or out. So this one is in. Okay, so this is part of the solution set. If we try 0, we get 0 squared minus 1, which is -1, which is not greater than 0. So that's out. Okay. And then finally, 2 squared minus 1 is 3, which is greater than 0. So this is in. Okay. And so our solution, or the domain of this logarithmic function, would be from -infinity to -1, union 1 to infinity. And of course, graphing the function, we should be able to see that between -1 and 1, there should not be any part of the graph. All right. So let's go ahead and graph this just to illustrate that. All right, so we had natural log of x squared minus 1. All right, I'm going to have to zoom back to the original. All right, and notice right here, okay, in between, I'm going to graph both positive and -1 as asymptotes. Right, and there we go. There is no function, or there's no part of the function that has values in between there because it's not part of the domain, but everywhere else there is. All right. So that's how we can go through and find the domain of a logarithmic sort of function. Okay. Again, all you're doing is just setting what's inside greater than 0 and then solving that inequality. Okay. So hopefully that's helpful for both seeing how to do it both algebraically as well as geometrically to find that domain.